Now let's talk about parametric and polar equations. These are two alternative coordinate systems to the rectangular system your students are used to seeing. Parametric equations appear complex, but they're actually quite simple if they're understood. Too much time and focus is spent on converting from parametric form to rectangular form, and this erroneously gives our students the idea that parametric equations are pointless and that they're just an extra step that we have to go through in getting to a rectangular equation that we're used to seeing. In fact, the parameter t in parametric equations serve a very important purpose and can really give us additional understandings that we wouldn't get from a regular rectangular equation. Parametric equations revolve around a third variable, the parameter, which generally does not show up when we graph or write solutions. In parametric equations, the x and y components are separate, which allows them to work perfectly for things like economics and physics and other real-world areas. It's important to show your students that the parameter, even though it doesn't show up in the solution, actually has a lot of value. So let's take a look at an example of a problem that would demonstrate that perfectly. Consider the following two parametric equations. First, x1 equals t plus 5, and y1 equals negative t squared plus 10. And the second one, x2 equals 5 minus t, and y2 equals negative t squared plus 10. If we convert these parametric equations to their rectangular form, you see that the equations end up being essentially identical. You can see that in the rectangular system, these two graphs are identical. But by converting them to rectangular equations, we've actually robbed them of some of their information. In equation 1, you can see that as t increases, x increases. However, in equation 2, as t increases, x decreases. In fact, if you consider t equals 0 to be sort of a starting point, then you can see that the graphs actually move in opposite directions as t increases. There are several ideas at play here. First of all, if there's a relevant domain for t, then that information needs to be converted over when we convert to our rectangular equation. More importantly, though, is that parametric equations can convey a sense of time, right? The point 2, 4 can have additional meaning in a parametric equation because we know whether that point came before or after other points on the graph. That information gets lost when you convert to a rectangular equation. Again, consider graph 2. We have a parabola, but it's essentially moving backwards. The points begin appearing on the right and move to the left, which is the opposite of what happens in graph 1. But see, this information is not something we can really convey with a strictly rectangular equation. We need that parameter t from the parametric equations in order to preserve that information. In math, we often don't get to spend as much time as we'd like doing hands-on activities with our students. That's doubly true when it comes to higher level courses like pre-calculus or trigonometry. So when it comes to polar equations, take this opportunity to really explore and let your students explore the unique nature of polar equations and help them to understand why polar equations are not only different, but can actually be better than rectangular equations. Again, like with parametric equations, if your focus is just on converting from one form to another, you're really missing out on the value and the interesting aspects of what make polar equations so unique and so important. A nice introductory activity is to explain the basics of polar coordinates to your students, r, theta, and then challenge them to create polar equations for the types of graphs they're already familiar with. They'll probably find that graphs like lines and circles are very easy to create in polar coordinates. Don't be afraid to discuss with your students how there may be certain basic shapes from our rectangular system that are either exceedingly difficult or even impossible to create as polar graphs. This will give them an introduction to the idea that they're going to see some new equations, new shapes as polar graphs, which cannot be replicated as rectangular equations. Of particular interest is either a horizontally or vertically shifted circle. These equations are very basic in polar coordinates, but if your students are familiar with the equation of circles in rectangular coordinates, they should find it somewhat intriguing that something that's so complicated and difficult in rectangular can be so simple in polar coordinates. This is a great opportunity to highlight to your students why physicists and engineers sometimes use alternate coordinate systems like polar to do their math in the real world. Because some things that may not be impossible in the rectangular system but are difficult can be much easier using an alternative system like the polar system. Also, may be worth mentioning to some of your more advanced students that there are two 3D versions of polar, spherical and cylindrical coordinates, both of which have some interesting applications as well. A final interesting idea to discuss with your students might be about the uniqueness of points in polar versus rectangular coordinates. Where a point in rectangular coordinates, like 5, 4, is unique, there are no other points that represent that place on the graph. In polar coordinates, that's not true. The points 5, 60 degrees and 5, 420 degrees, for example, are located in the same place.